All right, well, welcome back. Uh, Today, we're going to start talking about the arc length of a curve. So, first thing is to recall our basic idea uh, with the distance formula that if you have a pair of points connected by a straight line, then we can find their distance as the square root of the difference of the x's squared plus the difference of the y squared. Right. That's how the distance formula setup worked. Okay, so we want to do that for our uh, curve. So if we have some curve, let's say, just draw a horizontal line here, and let's say we have a curve that starts at the point A, and we're of course looking over the interval B. We're trying to find the length of the curve from A to B. So let's say that our curve maybe behaves something like that. All right, so we would like to measure the length of this curve. Length of this curve. So the process, remember, is to subdivide our interval. Remember, Sally. Sorry. Everything wants to pop up here today. Okay, so we subdivide our interval. So in particular, one of our subintervals at some point would be the interval from x sub I minus 1 to x sub I. Okay. Okay. And so on our interval, we would have our points. Sorry, I just distracted myself for a second there. And we want to measure that length. And so what we're going to do is we're going to approximate that length with a straight line. All right, so that's the second step. And we can find that length because this point up here would be the point x sub I minus 1, comma, f of x sub I minus 1. And this point over here would be x sub I, comma, f of x sub I. And so we can find that length for the subinterval, the approximate step. And that's what we want to do. And of course, once we have it approximated for one interval, then we're going to add them all up. All right, take the limit, which will transform us from a sum over to an integral. So the key step is really how we do this approximate step. So we're going to do that, and then we're going to make some adjustments. So let me zoom in here on this interval, right? This interval, and see what we have here with the distance formula. You can see how it kind of comes about. So in this triangle here, this temporary step, the difference, the width here, would just be the difference of the x values. So that would be x sub I minus x sub I minus 1. And we're actually going to call that delta xi. We're going to call that delta xi. Okay? And of course, the distance we're trying to find is the hypotenuse of our right triangle. We're going to call that d sub I. Well, then the height of this rectangle will actually be as a length, the absolute value of the difference between f of x sub I and f of x sub I minus 1. All right, and we're going to call that delta yi. Actually, it's not quite. This length is actually going to be the absolute value. Delta yi is actually just the difference. So I'm actually going to leave that off. Keep in mind, this length is actually positive, so I really should apply absolute value, but delta yi is just the difference, f of xi minus f of xi minus 1. Okay. And it's not going to matter whether this is positive or negative when we eventually put this stuff into our distance formula, because we're squaring it anyway. So it's not going to matter whether it's positive or negative. But just technically, if I was measuring the length of this side, it would actually be absolute value, but delta yi itself is actually the difference whether it's positive or negative. So I'm going to leave off the absolute value just so there's no confusion there. And then we would notice that di from the distance formula is just that difference. xi minus xi minus 1 squared plus yi, or f of x sub I, say it that way, f of x sub I minus f of x sub I minus 1 squared. But, as we've just discussed above, xi minus 1 is delta xi. And f of xi minus f of xi minus 1 is delta y. So we can actually rewrite di as the square root of delta xi squared plus delta yi squared. And then I'm going to do something to rewrite this, because right now this, how does it become an integral, right? That's our issue. How do we make this be something we can eventually transform into an integral? Delta xi is fine, that's dx. And now we have dx squared. What the heck? And then what's going on here with this y stuff squared? What's going on there? So to put this into a better format, particularly to get that what will eventually become dx outside of it, what we do is we factor out the delta xi squared from both pieces on the inside. Okay, and so that's going to give me the square root of delta xi squared times 1, and then we factor a delta xi squared out of the delta yi, but the delta yi squared doesn't have that. So we have to divide by delta xi. So we actually get delta yi over delta xi all squared. Okay. And then we can bring out the delta xi squared, the square root of delta xi squared. Square root of square would normally be absolute value, but by how we've set this up with our xi minus 1, delta xi is always positive. So again, square root of square is usually absolute value, but we can ignore that here because delta xi is always positive. And then on the inside, we're going to have the square root of 1 plus delta yi over delta xi squared. But we still have a problem with this thing if I take the limit of that. Right? So here's where the key step comes in. Here's where the key step comes in. This is a result that you've learned before. We actually used it when proving the fundamental theorem of calculus. And that was this. This delta yi over delta xi, remember, that is just f of xi minus f of xi minus 1. All of that over xi minus xi minus 1. Right? But remember, this thing here was the slope of the secant line. And we had a result that said for a nice function, a differentiable function, right, that the slope of the secant line is always equal to the slope of the tangent line for some point in that interval. So we're going to call that f prime of mi for some mi in the interval x sub I minus 1 to x sub I. And that is by the mean value theorem. So let me pause here for a moment and just go back over this mean value theorem and how we're making this change, because it's important to understand why this works. So if I jump back, I just got to go back through my notes here where I'm studying the mean value theorem. You may remember this result, Rolle's theorem. It said if you have an interval where the function value is the same on the two ends, then there's a place where you have a horizontal tangent line. Basically, that's just a special case because the secant line between A and B has a slope of 0, so we have to have a tangent line with a slope of 0. Right? And the conditions were that our function had to be continuous, meaning, again, no breaks or gaps, and differentiable, no sharp turns. Then we had the mean value theorem, which says just if f is continuous, differentiable, then there is a point in the interval right between your two endpoints. In this formula here, I stated it as A and B, where the derivative at some point is the same as the slope of the line between those 2 points, A f of A, B f of B, right? And so it's basically saying there's a time when the slope of the tangent line has to be the same as the slope of the secant line. And you can actually see that in this picture. Right, here I have a picture of a graph. I think it's actually just y equals x squared. And I'm looking at the point 0, 0, and I'm also looking at the point 3, 9 on that graph. And what I'm looking at here is there's my tangent line, or my secant line. And then what the mean value theorem says is if your function's differentiable and continuous, it's guaranteed to have a point where the tangent line is parallel to the secant line. In other words, the tangent line has the same slope as the secant line. And that's the result that we're using here. Okay, that allows us to now transition from this ugly thing that we have, and this delta yi over delta xi stuff. We can actually replace that with a derivative. We can actually replace that now with the derivative, giving my distance approximation, that the di, which we're now going to replace and call L sub I, the length of the ith subinterval, will be the square root of 1 plus f prime of m sub I squared with delta xi on the outside. So that's going to be our approximation step. We would then add all of those up. We would take the limit, and when we take the limit, the sum would become an integral. So the arc length formula is the integral from a to b of the square root of 1 plus. Now when we take the limit, the mi, it's actually going to just become every single point, right? When we do the limit, it's the size of the intervals go to 0. So that actually just becomes f prime of x squared, and delta xi becomes dx. And so now we have derived the formula for the arc length. We've defined the, say that again. We've found the formula for the arc length of a curve. So it turns out it's actually the square root of 1 plus the derivative squared, the integral of that stuff. Now, we're going to look at some examples, and what we're going to quickly discover is that because of this formula involving derivative squared on the inside of a square root, these often become integrals that are very difficult to do by hand. Some we'll be able to do later on, but a lot of these we will have to actually rely on our graphing calculator technology to be able to do that FNN stuff that I talked about in the previous section. Okay, so in the upcoming videos, we're going to look at some examples of computing some arc lengths, and again, some of them we will have to rely on technology. So until then.